This is Professor Steven Sakula, and I'd like to welcome you to this mini lecture, which will cover some of the material that I wasn't able to lecture on because of the wintry mix that has hit Dallas in the last couple of days. This miniature lecture is about complex distributions of electric charge, and specifically, what I'm hoping to teach you today is how to use calculus and Coulomb's law to handle more complicated distributions of charge. In the last lecture, we talked about the electric field around a single charge, and then we made our first complicated distribution, which was a pair of charges, that is a dipole, two oppositely charged but equal magnitude charge combinations. But what if we had 10 charges, or 1,000 charges, or Avogadro's number worth of charges? How would we handle that? Things get very complicated very fast as you start adding charges into the picture, and without a computer to do all the work for you, you can use some approximations and use some assumptions, and you can attack problems involving more complicated charge distributions using calculus and Coulomb's law. Now, one of the things that we talked about in a previous lecture, if you have a situation where you have a charge, and that charge has an electric field, let's denote that E vector, and that electric field, because this is a single point charge, is just given by Coulomb's law. So that's the constant k times the charge q over r squared, the distance r from the charge that you're measuring the field, times a unit vector r hat, which indicates the direction from the charge to where you are measuring the field. If you have multiple charges, then the total electric field is obtained simply from the sum of the individual electric fields. So let's give each charge an index I, and we'll sum over the charges from I equals 1 to n, where n is some finite number of charges. Now, if you have a small number, you could do this sum by hand. In fact, you can do this with the dipole. But what if you have a huge number of charges? Well, large distributions, let's draw something amorphous and blob-like here. Large distributions like this blob here, if we were to zoom in, we would see that in reality, this blob is made from many, many tiny point charges. So close together that you can't tell that they are separated from one another when you are looking at the whole macroscopic object. Since large objects are made fundamentally from point charges, we might imagine that if we found some way to sum up their electric fields, we would be able to get the electric field from the total. Let's imagine, in the language of calculus, that each point charge has a magnitude dq. Okay, so this is a differential of charge, a tiny, tiny, infinitesimal little piece of charge, our point charge. What would the electric field from that infinitesimal point charge look like? Well, we have the framework for that. We just have Coulomb's law. We have our constant. We have the distance from that charge that we're standing when we're measuring the field. We have the direction from the charge to us. And that's going to be its electric field, dE vector, where this is again meant to tell you that this is a tiny piece of a much larger electric field, and that tiny piece of electric field comes from a tiny charge. This is our building block. And through the language of calculus, we will be able to build up electric fields from complicated distributions with lots and lots of charges. Before we dive into that with an example, let's again review how it is that we connect the physics, that is, charge and the fact that it's the origin of electric field, to geometry, that is, the physical distribution of charge. Now, in physics, we make approximations. Those approximations can be appropriate in many situations, and they'll certainly be useful for us here in this course. One of those approximations is that if you have a line of charges, you can assume that they are uniformly distributed. And that means that it doesn't matter what piece of the line we look at, the charge per unit length is the same. Let's call that charge per unit length, or linear charge density, lambda. And if the line has a length L and a total charge capital Q, then the linear charge density lambda is just the ratio of Q and L. Now again, if this is uniformly distributed, we can look at any piece of this line, let's say a piece that has a length delta x, and we can count up the charge in that piece. We'll call that delta q. And again, that ratio will be equal exactly to lambda. Now, looking again at our tiniest little point charge, dq, our infinitesimal point charge, which takes up an infinitesimal piece of length of the whole line, dx. Again, if this is a uniformly distributed line of charge, then dq over dx should also be equal to lambda. This allows us to connect charge and geometry to some constant bulk property of the material, lambda, the linear charge density in this case. You may imagine that there's a similar quantity for two-dimensional surfaces that have a uniformly distributed charge. That would be sigma, the surface charge density, and that's the charge q divided by A, the area of the surface. And again, if it's uniform, then you can look at any piece of the area, we'll call it delta A, and the charge in that piece, delta q. And if we look at infinitesimal pieces of charge and the infinitesimal area dA that they take up, then again we can relate dq over dA to sigma. And you can imagine, again, extending this analogy to 3 dimensions, that we have a 3-dimensional charge density, a volume charge density, rho, and that's going to be equal to the total charge divided by the volume of this solid. And that if we look at any piece of the volume, delta V, and the charge inside of it, delta Q, that if it's a uniform charge density in the volume, we can relate rho to ratios of charge and the volume they occupy at all scales, including our most infinitesimal charge dq and the little volume dv that it occupies. So this is how you use physics to connect charge and geometry. And you're going to need to do that once you start having extended distributions of charge where you have to do things like integrals and you have to integrate over a geometric quantity. You need to be able to transform charge into geometry to do that. Let's think about an example that's almost real world. You have lots of copper wire in your house. It is the basis along which electrical transmission occurs in the home. It's in your walls. It runs from your laptop to the wall. There's copper everywhere. And copper, in your typical household application, is a thin wire, maybe a few millimeters wide, and very long. And we can imagine that the copper is itself made up of lots and lots of atoms, and those have lots of electrons around them. Some of those electrons are actually quite free to move. In fact, this is what makes copper such a good conductor, and we'll talk about that a little bit more later. Copper wire is a lot like a line of charge. If you were to stand far enough away from the copper wire, and if it were long enough, it would seem like a thin line whose thickness is negligible, but whose length is very large compared to its thickness. And so you can approximate that by saying that it's infinitely long. So let's actually sketch that problem out in one dimension. So here down in orange, I have my copper wire, and it goes all the way to negative infinity at the left and to positive infinity at the right. So we'll pretend it's infinitely long in both directions. It only occupies one dimension. It has a negligible thickness. I only drew this line thickness so that you could see that there was something here on the screen. So we're going to neglect its thickness completely. And what we want to do is we want to find the electric field, the total electric field from all the tiny little charges in this line at point P. So this is what we want to figure out. We want to figure out what's the electric field up here at point P. Now that point is in space someplace. We need a coordinate system. If we're going to start defining things relative to other things, we need a coordinate system. So to do that, let's define a Cartesian coordinate system. Let's make our wire the x-axis. Okay, so here's the x-axis. And let's put our point P on the y-axis. So let's go ahead and draw a vertical line, as vertical as I can make it, all the way down here through the x-axis. And here is our y-axis. And this is the positive j hat direction, and along the x-axis is the positive I hat direction. So there are some unit vectors to help us define our coordinate system directions. Okay, great, we have a coordinate system. What's the next step? Well, let's start simple. Let's start by looking at one infinitesimal piece of charge and the infinitesimal piece of the electric field that it contributes. I'm going to choose my charge to be right over here. So there's my little charge, dq. Now, let's remember what Coulomb's law is for this little guy here. It's going to be that his little piece of the electric field is equal to k dq over r squared r hat. Great. Well, we've got some pieces here we need to sort out. We need to get dq in terms of geometry. We need to figure out what our r vector looks like and what our unit vector looks like. If you attack these problems in pieces, you'll be very successful. So let's go ahead and do that. Now, the first thing I want to do is I want to define my r vector. I want it to go from dq to the place where I'm measuring the electric field. That's the definition of r vector. R vector. Okay, great. Now, let's think about this a second. It's got an x component. So here's Rx, and it's got a y component, Ry. Now, in terms of our coordinate system, this here is some positive distance x from where dq is located to the origin, where point P is located, and this is some positive distance y from, again, the origin up to the point P. So we can immediately write our vector in terms of our coordinate system. It's x I hat plus y j hat. That's our nice generic r vector. And that's pretty much as simple as we can make it right now. Now, what about r squared? Well, that's just the length of this r vector squared. So from the Pythagorean theorem, we know that r squared is equal to x squared plus y squared. So now we have r squared. That was pretty easy. Now the tricky part, the unit vector. This always seems to, feel like the worst part of the whole thing. But we have a nice, easy definition for the unit vector. We take the vector itself and we divide it by its length. Okay, well this isn't going to be too pretty, but it will be functional. So we have xi hat plus y j hat, and that's all over the square root of x squared plus y squared. Well, that's about as simple as we can make this thing right now. Okay, so there we go. There's our r hat. And we're missing only one piece. That is, we need to sort out what's going on with dq, because we don't quite know what to add up yet. I mean, how do you add up dq's using calculus? We don't know how to handle that. We need to get it into something that we can handle, and that is geometry. We need to relate q and geometry. And we can do that if this is a uniform distribution of charge. Then we know that it has a linear charge density lambda, and that is equal to the total charge over the total length of this line, which is infinite. But it doesn't matter what piece of the line we look at. If it's uniform, then we can choose to look at a little length of the line, dx, occupied by our little charge, dq. So we'll just draw that here. Here's a little piece of the total length of L. Its length is dx, and that's the length that dq occupies. Now we can relate geometry and charge. Now we can say that dq is equal to lambda dx. So we've got everything we need. We can start attacking this using calculus.